video series, we will work our way from the right to the left. That is, starting from your machine through the drivetrain towards the grid supply, just as the green bar under the diagram shows. In this video we will focus on the medium voltage drive. So what kind of medium voltage drive configuration do you need? Look to the drive as a black box converter. On the input side you have the grid supply with constant sinusoidal voltage and frequency, and on the output you want again a perfect sinus with variable voltage, variable frequency this time. The ideal black box does not influence your grid supply and it delivers a pure sine wave to your motor. Now, what does it take to deliver such superb power quality, and why does it matter? This is where the various types of medium voltage drive configurations called topologies come into play. The topology of the variable frequency drive combined with its filters determines the power quality of the power required for and delivered by the drive. Before getting into the nitty-gritty of topologies, let's get the basics right. We will for now only focus on the voltage source inverter, also known as VSI. In this basic diagram of a low voltage source inverter, there are basically three building blocks. Let's start with the rectifier, also known as the DFE direct front end, the intermediate circuit and the inverter. The voltage source inverter relies on capacitors in the intermediate circuit, and these capacitors create a decoupling between the rectifier and the inverter, and they compose also an energy buffer. In the third building block, often referred to as inverter, the DC voltage is recombined by the switching pattern of the IGBTs, insulated gate bipolar transistors, to a fundamental AC component with adjustable amplitude and frequency. In the topology slang, the terms pulses and levels are quite important. Back to the analogy of our drive as a black box, it is safe to say that the term pulses relates to the input side and the term levels refers to the output stage. Looking at our basic diagram, you notice that the output voltage will be created by connecting the plus and the minus at a switching frequency following a pulse width modulation pattern. This switching between two levels makes this a two-level drive. And yes, this is a three-level drive. Notice that the face-to-face output voltage of the three-level inverter is made out of 5 steps and is already looking much better than the two-level output voltage. Some manufacturers also offer a 5-level inverter, but it must be noted that if the 3 or 5-level inverters are to drive a standard motor that is not inverter duty, these inverters will require a sine wave output filter in order to reduce the common mode voltage and the voltage stress on the motor. These supplemental output filters can be of a significant cost and might also introduce performance restrictions on the power driver system. Moving further in our topologies overview and adding in more levels, you are now to discover the modular multi-level M2C MMC topology. Notice in the basic diagram of the modular multi-level inverter that the centralized DC capacitors are no longer present. Instead, we find capacitors for each power cell within the inverter part. The low voltage energy level stored in each cell results in an improved fault behavior as compared to other drive topologies. In the simplest case, such a power cell consists of 2 IGBTs and 1 capacitor bank. Medium voltage levels are obtained by adding together the outputs of multiple power cells. We can state that this drive delivers a superior sine wave output voltage and current, thereby eliminating harmonic heating and insulation stress on the motor, and reducing significantly the torque pulsations to levels lower than 1%. Next in our topology, overview is the two-level series connected multi-level cascaded H-bridge cells topology. What a mouthful. The multi-level cascaded H-bridge cells topology adds up the output of multiple low voltage power cells to obtain medium voltage levels. Each power cell is a simplified version of a standard two-level PWM low voltage converter. Many applications, including low voltage drives, use low voltage IGBTs. They are manufactured in very high quantities. Medium voltage drives that utilize low voltage devices can take an advantage of rapid innovation cycles, exceptionally reliable components, and a sustained availability of spare parts. The result of adding up the output of multiple low voltage power cells is a high quality output voltage providing less than 1% induced torque ripple, no need for an output filter for motor cable lengths even up to 2 km, a high reduction in common mode voltage, no derating on new or existing motor, no voltage spikes at the motor thanks to small output voltage steps, thereby indeed allowing the use or the reuse of a motor with standard insulations, ideal for retrofit. The integral dry multi-winding transformer provides for adaptability to available input voltage, clean input power thanks to the cancellation of the harmonics by the phase displacement in the secondaries. Multi-pulse inputs go from 18 to 54. Isolation from the grid, avoiding potential resonances and reducing impact from utility transients such as lightning and other equipment switching. This architecture, however, does not allow for regenerative operation or extremely quick deceleration. An active front-end version of this architecture is rarely economically viable. You can use this kind of drive for general purpose applications. For the more demanding applications with 4-quadrant and high dynamic response, you will need to look into the more advanced topologies. Let's go back to the analogy of our drive as a black box. We already stated that the term pulse relates to the input side. The rectifier bridge, connected to the capacitor, only conducts current at the peaks of the voltage waveform. That is when the AC voltage is higher than the capacitor voltage. So the AC input current waveform will contain bumps. In the basic diagram of a voltage source inverter below, you can actually see that we have 6 pulses in the rectified voltage UDC over one period of the mains voltage. In fact, when referring to a 6-pulse drive, we relate to a standard rectifier bridge containing 6 diodes, resulting in a 6-pulse DC voltage. The tree level depicted in this figure is made up of 2 6-pulse rectifiers supplied by a 3-winding transformer. We call this a 12-pulse in-feed. The secondary windings of this 3-winding transformer have a phase shift of 30 electrical degrees, thereby cancelling the harmonics, the 5th and the 7th, on the primary side. This 12-pulse in-feed results in lower line harmonic distortions. Indeed, the AC line input current of the 12-pulse drive looks already a lot better than the 6-pulse ones. The 12-pulse drive will generally not meet the requirements of voltage and current harmonic distortion imposed by current standards. Going for a higher number of pulses, such as 18, 12, 18, 24 or even 36, will further reduce the harmonic distortions, but this comes at a price for the rectifiers, the transformers, and at a higher footprint. An alternative to the architecture of characterized by the number of pulses is the active front-end AFE Instead of a rectifier or direct front-end DFE, we use basically a repeat of the inverter. The active control of the input stage enables a much cleaner input power and provides even for 4-quadrant operation. Finally, combining the modular multi-level version for AFE and for the inverter stage together realizes a high performance drive with clean in and output power.